All right, so now we're going to talk about our integrated rate laws. And this is going to show how our concentration changes with time. And the idea behind this and the equations might seem a little bit scary, but just hang in there. The application becomes more straightforward when we get to the end and I talk about it. But if you've taken integral calculus, yes, we mean that integration. We mean integral calculus integrated, okay? If you don't know what that means, it's okay, because you don't have to do it. It's not a prereq for the course, and it's not gonna, it's not gonna help you out too much. But what we're doing is we're integrating this definition of the rate right here to get a function of concentration with respect to time. That's what we're doing. So that integration is how we get from here to here. You don't have to know how to do that. What you have to know how to do is use these equations. That's it. And so how does concentration change with time? Well, it depends on if the concentration of a reactant is 0th, 1st, or 2nd order. And we're going to only do this in very simple situations where there is a single reactant. So our A plus B goes to C is too complicated for this example. So I have to bring in a new, even simpler chemical equation. X becomes Y. There we go. Boom. All right, that's our chemical equation. 1X becomes 1Y. We just zip over there. All right. So X is our reactant. So we're looking at change in reactant concentration with respect to time. Or actually, we're just looking at what it is at any given time. All right. And from this, we can get half-lives. And so there's how much we start with, how long till we have half of it left? How long till we burn through half of our reactant? Well, we get different relationships for whether it's 0th, 1st, or 2nd order. We're not even going to talk about 3rd order. And so being able to just solve these equations at any given time, so on and so forth. How much time till you have half left? Or if that is your half-life, what was your initial, or whatever it might be. Yeah, or you can use it to solve for K. So there's some variables we can play around with. But again, it's like I got to tell you all but one, you got to solve for the other. Now the other detail with this is when we plot these equations on graphs, depending on what our axes are. So we will do all kinds of mental yoga to get a straight line on the graph. And that's what we're doing here. So when we plot these on a graph, how do we get a straight line? Is it concentration of X versus T? Is it natural log concentration of X versus T? Or is it 1 over X versus T? Well, if these coordinates get you a straight line, 0th order. If these coordinates get you a straight line, 1st order. If these coordinates get you a straight line, it's 2nd order. So it's just what coordinates get me a straight line. And you notice it's always T on the x-axis, so it's basically, do I have X, do I have natural log of X, or do I have 1 over X? That's all you're looking for. And then if you are looking at one of these graphs, well, you can figure out what K is from your slopes. In the case where it goes negative slope in these two, got to multiply -1. Over here, you don't even have to do that. And then your initial value, well, you either have your initial concentration of X or the natural log of it, or 1 over it. Just depends on whether it's 0th, 1st, or 2nd order. And that's really all I'm expecting to be able to do. Use these graphs, use these understanding of these graphs, maybe solve half-life stuff. I know Smart Work will expect you to. And then be able to use these equations to find out what concentration will be at any given time. That's what you're doing. So you don't have to derive these equations. You don't have to do anything more than understand how to use them. That's all I'm looking for. So you don't have to derive them or anything. If you're bored, have fun, go for it. But if not, it's all right. If you're not that bored, that's fine. All right, so again, integrated rate laws. So before we talk about how concentration changes rate, now we're talking about how concentration changes over time. That's the difference. So I might have misspoke a little bit earlier. I was saying it had to do with rate changing over time. We'd already talked about that. I was just out in, I don't know, a world where you could have other people in this room right now or something. Who knows? Imagination land. All right. So that's kind of the idea behind integrated rate laws. It's a little bit tricky. Make sure you understand the rate laws we talked about first before you really dive into this, because they are separate ideas. Don't let the similarity of the names fool you. They're very different ideas. They'll tell you the same stuff, but they go about it a totally different way. So just take them one at a time. That would be my advice. All right, so next we're gonna talk about how temperature changes reaction rate. Introduce the Arrhenius equation. And then we'll have a little bit more of the chapter to do. And then that'll be it for the second to last chapter of this class.